project is on Canny edge detection, which is used to detect edges in an image. As you can see here, it consists of 4 stages: Gaussian blur, Sobel, non-max suppression, and double thresholding. A common computation we do across all our kernels is convolving our image with 5x5 or 3x3 filters. For example, in our Gaussian kernel, we use a 5x5 filter to convolve with every single pixel and create a sum that we store in that specific pixel. So if you look at pixel 0, some of these pixels go beyond the image boundary. To accommodate this, we can use shared memory tiling with a halo radius of 2 pixels to be able to compute that sum. The additional benefit of using shared memory tiling is it avoids expensive global memory accesses. Pixel 34 pixels that are needed for its computation are within the boundaries of the image. However, it and pixel 0 share 9 pixels, and this eliminates the need for expensive global memory accesses. Here's how we load our shared memory. Every thread loads its own pixel ID in the strided access pattern, and the stride is 256. So thread 0 loads this pixel, and so on. Our initial iteration of our kernels consisted of 16 by 16 grid, where each thread in our 256 threads computes its own pixel. We iterate on this in the future, as we talk about later in this recording. Here is how we computed our boundary pixels. So if you have a 16 by 16 image, the shared memory tile would exceed the 16 by 16 image. The way we resolved any potential distortions is by pinning the boundary pixels to this closest pixel.
In our second approach, we wanted to ensure that we would get more outputs per thread. Therefore, we expanded our tile size to 32 by 32 pixels, and now instead of having one thread do computation for 1 pixel, we have each thread doing computation for 4 pixels at a time. That can be seen in the depiction of each of the colored squares. That is the amount of computation that one thread is doing. Now, the red box around this section represents 1 warp, or 32 threads. So with this kind of memory access pattern, we discovered that by having each thread do 4 pixels in a 2 by 2 square, that would result in several bank conflicts. As you can see, within just this warp, we get several bank conflicts as indicated by these red squares. Here, we have thread 0 and thread 16, both accessing the same data in the same bank, leading to a bank conflict and decreased performance. Overall, these kind of performance slowdowns end up cascading when the image size is increased due to the fact that we're calling multiple kernels consisting of this kind of memory access pattern. In our final design, we're still using a 32 by 32 pixel tile size. However, this time, we're now instead using a strided memory access pattern in order to reduce bank conflicts. Here you can see that we have 32 threads, each with their own colors, and the key thing to note here is that each thread is managing its own bank. So for example, thread 0 is located here, 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 and here. No bank conflicts. This results in improved performance and really good speed up gains, which you'll be able to see in our results slides.
I'll briefly explain our Gaussian implementation. So the Gaussian image smoothing algorithm is an image smoothing algorithm that uses this function to calculate certain weights. And the point of it is to use a 5 by 5 filter around a pixel and assigns weights to those neighboring pixels, and then computes a weighted average for the center pixel. And the point of why we use Gaussian is because each computation of a pixel, it can be parallelized because they're all independent operations. And we designed our program to have each thread calculate 4 pixel computations when it runs. So this is our graphical analysis of our Gaussian blur algorithm. We tested across different image sizes, as you can see here. And the way we measured our performance was using CUDA events, and we compared it to the benchmarking RTDSC calls, and we converted the RTDSC to seconds. And then, as you can see for the small image, the speed up is relatively low, and this is because for our small image, we designed our thread block to be perfectly encapsulated at 32 by 32, so it's only one thread block being called. And in this case, the cost of parallelism is higher than the number of computations happening. But if you go to the extra large image, we have much more computations, and this exceeds the cost of parallelism, which is why we have such a great performance here. Another important feature is that, as you can see, as the image grows, we get diminishing returns from large to extra large. And also within a larger image, we have multiple calls to multiple thread blocks being launched, which is why the performance is much better compared to just one thread block being launched. So let's get into our Sobel explanation. So here, the Sobel algorithm is basically having two box filters this time that we will convolve each pixel with. But these filters are 3 by 3 instead of 5 by 5. And the point of this is to calculate the x gradient and the y gradient for each pixel. And then once we do that, we return the magnitude and the gradient or the angle itself in two different arrays that are passed into the next stage, which is not maximal suppression. And with the Sobel algorithm, we are returning the vertical and horizontal, like distinct edges within an image. This is our Sobel performance graph across the same images. And as you can see, the raw numbers of our speedups here are actually much higher than the Gaussian speedup numbers. That is because the number of computations that we're doing is much less, because we're doing a 3 by 3 filter instead of a 5 by 5 filter that we did on the Gaussian. And also another key observation is that the speedup actually decreases when we go from large to extra large, and that's also because of the 3 by 3 versus 5 by 5 difference. Because we're doing much less computations, the GPU is more bounded by memory than the actual computation itself, which is why we have a decrease here.
The third stage of our Canny edge detection pipeline is non-max suppression, which essentially takes all the different edges detected from the Sobel gradient stage and suppresses them to make them thinner and cleaner. Now, the way this algorithm works is it looks at the gradients generated from the previous step, and then it quantizes them in 4 different directions: horizontal, vertical, left diagonal, and right diagonal. And essentially, for each pixel, what happens is, if we figure out that this one is quantized in the horizontal direction, the algorithm will then compare this pixel with the ones by its side and find the max one and suppress the ones that are smaller. This results in the thinning of edges and results in a cleaner output, such as this. So the speed up we notice from non-max suppression results from the fact that each computation in non-max suppression is also independent. So using both the gradient matrix and the magnitude matrix, one pixel is not dependent on the outputs from any other pixels, except from those in the Sobel kernel stage. Therefore, we see these large speedups very similar to the speedups we noticed in our Sobel stage.
Here is the last stage of our Canny pipeline, double thresholding. In the double thresholding algorithm, you have a high gradient value, a magnitude value, and a low magnitude value. Pixels whose magnitude exceeds the high level are considered strong edges, and they are preserved in the final output image. Pixels whose magnitude are below the low threshold are considered weak edges and are discarded. However, intermediate pixel values that are in between inspect their neighbors' pixel magnitudes, and if any connecting neighbors and edges contain a pixel with a high magnitude or a strong edge, those pixels are preserved as well. Here is our final result for our double thresholding algorithm. As you can see, the same trend from the past 2 graphs continue, where small has a slowdown. However, as you keep increasing the image size, the speed up continues. and it diminishes from large to extra large. This is because double thresholding also uses a 3x3 kernel, which it only uses for its final step of identifying if you are a intermediate edge and if you need to be promoted to a strong edge.
Lastly, I want to cover the difference between the GPU raw performance of the full pipeline versus the full pipeline with the GPU including the CPU overhead. So in both graphs, you can see that the speed up gets larger with larger images, but more importantly, the raw speed up number is much higher when you just look at the GPU compared to the CPU overhead that's added here. And this is because the CPU overhead includes dynamically allocating memory for the image, and also sending the image data to the GPU for it to produce computation and then sending it back, which significantly is slower than just the GPU.